Welcome. Today we're diving into our solar system, taking a really detailed look.
Yeah, we've pulled together quite a bit of info, trying to give you a solid picture of, well, our cosmic neighborhood.
Exactly. The goal is to hit the highlights, the really fascinating stuff about how it all fits together.
Right, without getting totally lost in the weeds. There's so much detail, but we want the big picture, the important connections.
And just setting the scene, it's staggering to think how old this place is. What is it, about 4.57 billion years?
Roughly, yeah. 4.5682 billion, give or take a tiny fraction. And we're sitting here in the Milky Way.
In our own little corner. The local interstellar cloud, I think.
That's the one. Inside the local bubble, all tucked away in the Orion arm of the galaxy. Quite an address.
So let's start at the beginning. Formation. It all kicked off with a giant cloud collapsing.
Pretty much. About 4.57 billion years back, you had this immense cloud of gas and dust just starting to pull itself together. Gravity doing its thing.
Okay, and as it collapses, it starts spinning faster, right? I vaguely remember something about that.
That's the conservation of angular momentum, like a figure skater pulling their arms in.
Ah, okay.
The cloud shrinks, spins faster, and flattens out. That creates the protoplanetary disk around the center.
And that dense center that eventually became the sun, but not instantly. There was a phase before it properly ignited.
Right, the proto-sun. It was probably a T-Tauri star for a while.
T-Tauri. What does that mean exactly?
They're young stars still gathering material from the disk. They're pretty active, strong stellar winds, lots of energy output, but not yet fusing hydrogen in the core.
Okay, so it's gathering mass, heating up, and then comes the main event. Fusion starts.
Exactly. The core gets hot enough, dense enough, hydrogen atoms start smashing together to make helium. Bang! Huge energy release.
And that's our sun, the G2V star we see today. A yellow dwarf.
That's the moment it joins the main sequence, and it's been burning pretty steadily ever since, mostly.
Mostly. So it's changing over time. I heard its brightness is increasing slowly.
It is, yeah. Very gradually getting more luminous, and that process continues.
Which has pretty big consequences down the line, right? For us, for the planets.
Oh, absolutely. Eventually, in maybe 7 billion years or so, it'll run out of hydrogen fuel in its core.
And then?
Then things get dramatic. It starts fusing hydrogen in a shell around the core and helium in the core itself, and it expands massively. Becomes a red giant.
A red giant. That sounds bad for the inner planets. Mercury and Venus are goners.
That's the current thinking. It'll likely swell up enough to completely engulf Mercury and Venus. Earth, well, Earth's fate is a bit more uncertain.
Might survive. Or just get totally roasted.
Even if it's not swallowed whole, the surface will become incredibly hot. Way too hot for life as we know it. It really shows how a star's life cycle controls everything.
Wow. What a finale. But wait, that's not the absolute end for the sun itself, is it? Planetary nebula, white dwarf.
Right. After the red giant phase, the sun puffs off its outer layers. That creates this beautiful structure, a planetary nebula. And what's left behind at the very center is the core, a super dense, hot white dwarf, which will then just slowly cool down over trillions of years.
Incredible. Okay, so back to the present-day solar system. The structure. The sun is clearly the boss mass-wise.
Oh, yeah. It's got, what, 99.866% of all the mass? Everything else is just leftovers, really.
All the planets, moons, asteroids. Just a tiny fraction.
Barely registers on the scale compared to the sun.
And how things are arranged. Most planets orbit in roughly the same flat plane, the ecliptic.
That's right. It's a leftover from that spinning protoplanetary disk flattening out. Very neat, mostly.
Mostly, so there are exceptions.
Definitely. Things like comets and a lot of objects out in the Kuiper Belt, they can have orbits tilted way off that plane. Gives the whole system a bit more of a 3D feel when you include everything.
And they mostly go around the same way, too. Counterclockwise if you're looking down from the sun's north pole.
Yep, another relic of the disk's original spin direction.
But again, exceptions. I seem to remember Halley's Comet is weird.
It is. Halley's goes around the wrong way, a retrograde orbit. These oddballs usually tell you something interesting. Maybe they came from somewhere else or got knocked around gravitationally.
Right. And the spacing between the planets. It seems to get bigger the further out you go.
Generally, yes. The gaps increase. People tried to find a mathematical rule for it, like the Titius-Bode law.
Ah, yes, I've heard of that. Did it work?
Kinda. It worked okay for the inner planets up to Uranus. sort of, but it completely misses Neptune, and there's no real physical reason why it should work. So it's more like a historical curiosity now.
Okay, so no perfect pattern. And the orbits themselves, they follow Kepler's laws, right?
Yeah.
Not perfect circles.
Correct. Kepler figured out they're ellipses with the sun at one focus.
And they speed up when they get closer to the sun.
Exactly. A planet sweeps out equal areas in equal times, meaning it moves faster at perihelion, its closest point to the sun, and slower at aphelion, its farthest point. Really fundamental stuff for understanding how everything moves.
Okay, great overview. Let's zoom in now. The inner solar system, the rocky guys, and the asteroid belt.
Right, the terrestrial zone. Hotter, closer to the sun, where rock and metal could condense easily.
Starting right next door. Mercury, smallest planet, no moons. What else stands out?
Well, it's heavily cratered, like our moon, shows its age, billions of years of impacts. But it also has these unique features, lobate scarps.
Scarps, like cliff.
Yeah, big wrinkles on the surface. The thinking is they formed as the planet's huge iron core cooled and shrank, making the crust buckle.
A shrinking planet. And that core is unusually large, isn't it?
Very large relative to the planet's size. Why that is, still debated. Maybe a giant impact stripped away some of its outer layers early on.
In a really thin atmosphere just blasted off by the sun.
Pretty much, yeah. Just a tenuous exosphere from solar wind stripping and maybe some outgassing.
Okay, next out. Venus. Earth's sister in size, but wow, so different.
Totally different path. Similar size, density, probably similar internal structure, iron core, silicate mantle. But the atmosphere.
It's insane, right? Super thick CO2.
About 90 times Earth's surface pressure. Almost entirely carbon dioxide, which led to a runaway greenhouse effect.
Making it the hottest planet, even hotter than Mercury.
Oh, yes. Surface temperatures over 400 degrees Celsius. Hot enough to melt lead. No moons either. And maybe active volcanoes keeping that thick atmosphere topped up. It's a cautionary tale about planetary climates.
Definitely. Then, thankfully, we get to Earth. The biggest rocky planet, densest too.
And unique, as far as we know. Liquid water, active plate tectonics, constantly recycling the crust.
And the oxygen atmosphere, thanks to life.
A direct biosignature, yeah. Plus, our unusually large moon.
Which is pretty important, isn't it? Stabilizing our tilt.
Hugely important. Helps keep our climate relatively stable over long periods, drives tides. We're quite lucky, really.
Okay, moving out again. Mars, the red planet. Smaller, thinner atmosphere.
Yeah.
But so much fascination.
Mars captures the imagination, doesn't it? That thin CO2 atmosphere, maybe 0.6% of Earth's pressure, but the geology, wow.
Like Olympus Mons, the giant volcano.
The biggest volcano in the entire solar system, and Valles Marineris, that enormous canyon system that dwarfs the Grand Canyon.
And the signs of past water.
Everywhere. Dried riverbeds, lake deltas, minerals that only form in water, even subsurface ice now. It was clearly a different place billions of years ago.
Hence the search for past life.
Yeah.
And its red color, just rust.
Basically, yeah. Iron oxide in the dust and rocks. And it has two tiny moons, Phobos and Deimos.
Captured asteroids, probably.
That's the leading theory. They look like asteroids, irregular shapes. Mars likely grabbed them gravitationally long ago. It's the planet we've studied most after Earth.
Right. And then, between Mars and Jupiter, the asteroid belt.
That's the zone. Roughly 2.3 to 3.3 AU from the sun, full of rocky bodies.
Is it crowded like in sci-fi movies? Dodging rocks constantly?
No, not at all. Space is huge. The asteroids are millions of kilometers apart on average. You could fly through and likely not even see one up close unless you aimed for it.
Okay, good to know. So they're leftovers. Planetesimals that never formed a planet.
Exactly. Jupiter's immense gravity nearby kept stirring things up, preventing them from clumping together into a larger body.
How many are there? How much mass?
Tens of thousands, maybe millions bigger than a kilometer. But the total mass is tiny, less than 1,000th of Earth's mass.
Wow, really spread thin. And they're not all the same. There are groups and families.
Yeah, based on their orbits and composition. Some groups seem to be fragments of larger asteroids shattered by collisions. Some even have their own tiny moons.
Asteroid moons. That's cool. And some are like comets.
Main belt comets, yeah. Icy bodies in the belt that sometimes show tails. They might have been a source of Earth's water.
And the Trojans. They're not in the main belt.
Nope. They're in Jupiter's orbit. Trailing ahead and behind it at the Lagrange points these gravitationally stable spots, like cosmic parking spaces.
Fascinating. And the biggest thing in the main belt is Ceres, right? The dwarf planet.
That's right. Ceres, nearly 1,000 kilometers across, big enough for its own gravity to make it round.
It got promoted from asteroid, demoted from planet, now a dwarf planet.
Yeah, its status changed as our definition evolved. It was discovered first, thought to be the missing planet between Mars and Jupiter, then more asteroids were found. Then in 2006, the IAU reclassified it as a dwarf planet alongside Pluto. Shows how science progresses.
Okay, that covers the inner region. Time to head outwards, past the asteroid belt. To the giants.
Into the realm of the gas giants, their huge moon systems, rings, and then the really icy stuff beyond. A whole different solar system out there.
Starting with the undisputed king. Jupiter, just massive.
Unbelievably massive.
Yeah.
318 times Earth's mass, more than twice the mass of all the other planets combined, mostly hydrogen and helium.
Almost a failed star.
In a way, yeah. If it had been maybe 80 times more massive, it could have ignited fusion. It actually radiates more heat than it receives from the sun because it's still slowly contracting.
And that heat dries its crazy atmosphere. The bands, the Great Red Spot.
Exactly. High internal heat, rapid rotation creates those distinct cloud bands and huge swirling storms. The Great Red Spot is an anticyclone wider than Earth that's been observed for centuries.
Incredible. And moons. Loads of them.
95 confirmed so far, including the big four Galilean moons Io, Europa, Ganymede, Callisto, discovered by Galileo.
And they're worlds in themselves, right? Volcanic Io, potentially ocean-bearing Europa.
Absolutely. Io is the most volcanically active body in the solar system. Europa likely has a huge saltwater ocean beneath its icy shell. Ganymede is bigger than Mercury. Callisto is ancient and cratered. And Jupiter has rings too, faint ones.
Wow. Okay, next out is Saturn, the one with the really famous rings.
Saturn. Instantly recognizable, another gas giant, similar composition to Jupiter, hydrogen and helium mostly.
But much less dense. I heard it could float in water if you had a big enough bathtub.
Theoretically, yes. Its overall density is less than water. It's got about 60% of Jupiter's volume, but less than a third of the mass.
And those rings, what are they made of?
Billions and millions of particles, mostly water ice, ranging from dust specks to chunks the size of houses, maybe even mountains, all orbiting Saturn in an incredibly thin plane.
Just spectacular. And moons, lots of those too.
Even more than Jupiter currently, 146 confirmed moons. Titan is a huge one, bigger than Mercury, with a thick nitrogen atmosphere and lakes of liquid methane.
Liquid methane lakes.
Yeah, and then there's Enceladus, a smaller icy moon that shoots geysers of water, ice, and vapor into space from cracks near its south pole. Suggests a subsurface ocean there, too.
Amazing. Okay, further out still. The ice giants. Uranus.
Uranus. It's different from Jupiter and Saturn, still massive, about 14 times Earth's mass, but it has more ice as water, ammonia, methane, mixed in with the hydrogen and helium.
And it's tilted on its side, like it got knocked over.
Exactly. Its axis is tilted by about 98 degrees relative to its orbit. It basically rolls around the sun on its side, probably the result of a giant impact long ago.
Weird seasons then. And it's colder.
It has a much colder core than the other giants, radiates very little internal heat, makes its atmosphere look a bit bland in visible light, kind of a hazy blue-green. It has 27 known moons, named after characters from Shakespeare and Pope, and faint rings.
Okay. And the last official planet, Neptune.
Neptune. Similar in size to Uranus, maybe slightly smaller, but actually more massive, about 17 Earth masses, so it's denser.
And it's blue, a really vivid blue.
Yeah, methane in its upper atmosphere absorbs red light, giving it that striking color. Unlike Uranus, Neptune does radiate significant internal heat, more than twice what it gets from the distant sun.
So it's more active. Storms.
Yes, it has some of the fastest winds in the solar system and had a prominent great dark spot when Voyager 2 flew by, though that seems to have dissipated now. It has 14 known moons.
Any standouts?
Triton is the big one. It's likely a captured Kuiper belt object because it orbits Neptune backwards, retrograde, and it's geologically active, with cryovolcanoes spewing nitrogen, frost, and gas.
Captured. So it wasn't originally formed there.
Probably not. Neptune also has its own set of faint rings and Trojan asteroids like Jupiter.
And what about Planet 9? Is that still a thing? The hypothetical big one way out there.
The hunt is definitely still on. The orbits of some extremely distant objects seem to be gravitationally clustered in a way that suggests a large planet, maybe 10 times Earth's mass, is shepherding them.
Way, way out.
Yeah, maybe orbiting 20 times farther out than Neptune on average, in a huge eccentric orbit taking 10,000 or 20,000 years. But it hasn't been seen directly yet. Still a compelling hypothesis, though.
Okay. Beyond the planets, we get into the realm of smaller icy bodies. Comets first. the ones with tails.
Right. Comets are basically dirty snowballs a few kilometers across, typically, mixtures of ice, dust, and rock.
And they loop in from far away.
They have highly elliptical or eccentric orbits. When they swing into the inner solar system, the sun's heat vaporizes the ice's sublimation.
Creating the fuzzy head, the coma?
Exactly.
Yeah.
And the solar wind and radiation pressure push that gas and dust away, forming the tails, usually one dust tail and one ion gas tail, pointing away from the sun.
Where do they come from? Kuiper belt. Oort cloud.
Both. Short-period comets, with orbits less than 200 years, mostly come from the Kuiper belt, or the scattered disk. Long-period comets, with orbits of thousands or millions of years, are thought to originate in the much more distant Oort cloud. Some might even be interstellar visitors just passing through.
And old dead comets can look like asteroids.
Yeah, once all their volatile ices are gone, they can become inert, rocky bodies, hard to distinguish from asteroids.
Interesting. And then there are centaurs, kind of halfway things.
Centaurs orbit between Jupiter and Neptune. They're icy bodies, likely escaped Kuiper belt objects, and they show characteristics of both asteroids and comets.
Like Chiron showing a coma.
Exactly. And Chiriclo, the largest known centaur, even has its own ring system. Very unexpected.
Wow. Okay, now we're properly beyond Neptune. The trans-Neptunian objects, or TNOs.
A huge region, mostly populated by small bodies made of rock and ice. It includes the Kuiper belt and the scattered disk.
So the Kuiper belt is like a bigger, icier asteroid belt.
In a way. It's a ring or donut of debris, mostly ice, extending from about Neptune's orbit, 30 AU, out to maybe 55 AU?
How many things are out there?
Probably over 100,000 objects bigger than 50 kilometers across. But again, like the asteroid belt, the total mass is surprisingly low, maybe a tenth to a hundredth of Earth's mass.
And many have moons and weird orbits.
Yes, quite a few have moons, and many have orbits that are quite inclined, tilted relative to the main planetary plane, and eccentric.
It's divided up. Classical objects and Plutinos?
Right. The classical KBOs or cuboanos have relatively stable near-circular orbits that aren't strongly influenced by Neptune. Then there are resonant objects, like the Plutinos, which are locked in a specific orbital ratio with Neptune.
Like Pluto itself, the most famous Kuiper belt resident.
Exactly. Pluto is in a 3.2 resonance with Neptune. It orbits twice for every 3 Neptune orbits. This actually prevents them from colliding, even though Pluto's orbit crosses Neptune's path.
And it's a dwarf planet now, largest known KBO. Eccentric, inclined orbit.
Yeah. It has 5 moons. Charon is the biggest, almost half Pluto's size, so they're sometimes called a double dwarf planet system. Then 4 smaller ones, Nix, Hydra, Kerberos, and Styx. New Horizons gave us amazing views.
And there are other dwarf planets out there too. Haumea, Makemake.
Yes, Haumea is fascinating. It's shaped like a squashed rugby ball or a ellipsoid, probably because it spins incredibly fast, about once every 4 hours, likely due to a past collision. It has 2 moons and a whole family of smaller KBOs associated with it.
A collision family. And Makemake.
Makemake is another big one, second brightest KBO after Pluto. It's a classical KBO, quite reddish in color, and has 1 known tiny moon. Also high inclination, eccentric orbit. Orcus, Macquarie are other significant ones too. It's a busy place.
Okay. Beyond the main Kuiper belt, the scattered disk.
This region overlaps the Kuiper belt, but extends much, much farther out. Objects here were likely scattered by Neptune's gravity long ago, flung into these very large, highly eccentric and inclined orbits.
Is this where some comets come from too?
It's thought to be a major source of short-period comets, yes. Some people just consider it part of the Kuiper belt scattered KBOs.
And Eris lives out here, the dwarf planet that caused all the fuss.
Eris is the most massive known dwarf planet, slightly more massive than Pluto, though slightly smaller in diameter. It's definitely a scattered disk object. Its orbit is extremely eccentric and inclined, taking it way out, almost 100 AU at its farthest.
Its discovery really forced the issue on defining planet.
It did. Finding something potentially larger than Pluto way out there made astronomers rethink the categories. Eris has 1 moon, Dysnomia.
And we keep finding things even further out. Gong Gong, far out, far out.
Yeah, pushing the boundaries. Gong Gong is another dwarf planet candidate. Far out, around 120 AU, and far out even further, are examples of these extremely distant TNOs, detached objects, possibly influenced by Planet 9 if it exists, or maybe galactic tides or passing stars. They really test our models.
Okay, now really zooming out. The heliosphere, the sun's bubble.
Right. The solar wind, that stream of charged particles from the sun, blows out into space and creates this huge bubble, the heliosphere. It pushes back against the interstellar medium, the gas and dust between stars.
How far does it go?
Roughly 100 AU, maybe a bit more, depending on the direction. It shields the inner solar system from a lot of galactic cosmic rays.
And there are boundaries within it. Termination shock, heliopause.
Yes. The termination shock is where the solar wind abruptly slows down from supersonic to subsonic speed as it starts hitting the interstellar gas. That's around 85-95 AU out.
And the heliopause is the edge.
The heliopause is the actual boundary where the solar wind pressure balances the pressure of the interstellar medium. Beyond that is interstellar space. It's maybe a 110, 120 AU out.
And the Voyager probes went past these.
They did. Voyager 1 crossed the heliopause in 2012, Voyager 2 in 2018, humanity's first direct sampling of interstellar space. The region between the shock and the pause is called the heliosheath.
Incredible achievement. Beyond the heliopause, the Oort cloud. Still hypothetical.
Still technically hypothetical, as we haven't directly observed it in place, but the evidence from long-period comets is very strong. It's thought to be this vast spherical cloud of trillions of icy bodies surrounding the solar system.
How far out?
Really far, maybe starting thousands of AU out and extending to 50,000 AU, 100,000 AU, possibly even further. That's like a light year or more, almost halfway to the nearest stars.
Wow, so these are remnants scattered out by the giant planets early on.
That's the idea. They're very loosely bound by the sun's gravity. Galactic tides, passing stars, giant molecular clouds can perturb their orbits and send them falling inwards as long-period comets.
And Sedna, that weird object. Does it fit in here?
Sedna is really interesting. It's large, reddish, and has this incredibly elongated orbit that takes it from about 76 AU out to nearly 1,000 AU. Its perihelion, its closest point, is too far out to be explained easily by scattering from Neptune.
So maybe it's part of an inner Oort cloud.
That's one possibility. A population of objects beyond the scattered disk, but not quite in the classical Oort cloud. Its existence, and others like it, points to perhaps complex dynamics in the early outer solar system, maybe involving passing stars or that elusive Planet 9.
So much still unknown out there. The gaps between these regions, hypothetical volcanoids inside Mercury's orbit, even Nemesis, the sun's Death Star companion.
Well, the search for volcanoids hasn't found anything conclusive yet. It's tough looking so close to the sun. The Nemesis idea, a distant stellar companion causing periodic extinctions via comet showers, hasn't really panned out based on current evidence, but people keep looking for very distant objects. The space between the Kuiper Belt and Oort cloud is definitely a vast, unexplored frontier.
Okay, last piece. Putting it all in galactic context, we're in the Milky Way.
Yep, our home galaxy. We're located in one of its spiral arms, the Orion Arm, or Orion Spur.
How far from the center?
About 27,000 light-years out from the supermassive black hole at the galactic core.
And we're moving, orbiting the galaxy.
We are. The whole solar system is whipping around the galactic center at about 240 kilometers per second. It takes us roughly 225 to 250 million years to complete one orbit, sometimes called a galactic year.
250 million years, and we bob up and down too.
Yeah, relative to the galactic plane.
Yeah.
We cross the plane roughly every 35 million years as we orbit.
Does our location matter, being out in the spiral arm?
Probably. It's a relatively quiet region compared to closer to the center or deep within a major spiral arm. Less risk from things like supernovae or intense radiation from the galactic core might have helped life develop here.
In their local neighborhood. The local interstellar cloud, local bubble, nearest stars.
We're currently moving through the local interstellar cloud, which is just one small cloud within the much larger local bubble, a region of hot, low-density gas likely carved out by past supernovae.
And the neighbors.
Nearest star system is Alpha Centauri, about 4.3 light-years away. That includes Proxima Centauri, technically the closest single star right now. Barnard's star is next closest lone star, about 6 light-years off.
So thinking about this whole journey, from the collapsing cloud to our place in the galaxy, it's just immense.
It really is. The scale, the complexity, the sheer variety of worlds and objects shaped over billions of years. From the fusion furnace of the sun to icy bodies barely catching its light, all dancing to the tune of gravity.
We've covered the formation, the structure, the inner rocks, the outer giants, the belts, the distant reaches, even our galactic home.
It's a dynamic system, constantly changing, constantly being explored. Jupiter's storms, Enceladus's geysers, the slow migration of objects is far from static.
Which leads to a final thought, perhaps. Even after all this exploration, all these discoveries, there's still so much we don't know, isn't there?
Absolutely. Every answer seems to lead to more questions. What's really going on under the ice of Europa or Enceladus? Does Planet 9 exist? What lies in the true depths of the Oort cloud? How unique is our system, really?
It really makes you think. We're still mapping our own cosmic backyard, constantly surprised by what we find, constantly refining our understanding. It just spurs you on, doesn't it? To keep looking, keep asking, keep digging into what we know and what mysteries remain out there in the dark.
Okay, think for a moment about standing barefoot on the earth. Feel the give of the soil, maybe coolness of grass, or just hard rock.
Yeah.
Now, let your mind go outwards. Imagine the endless blue ocean just stretching out.
Right, the vastness.
And just notice your breath, the air you're breathing, this envelope around the sphere we live on. You've probably felt that flicker of curiosity about this place, Earth, our home. And, well, you're not alone.
Absolutely. It's so easy to just go through our days, isn't it, without really thinking about the wonder of the planet right beneath us.
Exactly.
We're all just passengers on this giant rock hurtling through space and its story.
Wow. Its essence is far more captivating than most people realize.
And that's exactly what we're diving into today. We've pulled together a huge amount of information, like a real treasure trove of knowledge. And our goal is to pull out the most, well, mind-blowing, the most fundamental stuff about Earth.
Getting to the core of it. Yeah, think of it as really getting a handle on the world around us. Finding those essential truths that, often get lost day to day.
And we're talking a history stretching back, 4.54 billion years? It's almost. Saying that the number feels abstract, doesn't it?
It really does.
And in that enormous stretch of time, just a dizzying number of events have shaped our planet, from its fiery birth to, well, the distant, almost unbelievable future scenarios.
Exactly. And look, while the sheer amount of info can feel a bit much,
it can.
Our aim is clarity, those aha moments. We're not trying to get bogged down in, endless details. We want to light up the key points, the really surprising stuff, and hopefully offer a totally fresh look at something we might take for granted.
Sounds good.
Okay, let's really dig in, shall we? Where else to start but the very beginning? Earth's genesis.
Right. So our best understanding points to a start within a solar nebula, this colossal cloud of interstellar dust and gas, kicking off around 4.54 billion years ago.
A nebula, okay.
But what's really amazing is the likely trigger for this cloud collapsing.
Yeah.
A shockwave.
A shockwave.
Yeah, from a nearby supernova, the explosive death of a massive star light years away.
Wow.
Just imagine that for a second. The energy from this huge cosmic explosion basically starting the formation of our whole solar system.
Talk about a dramatic start. So this shockwave kicks things off. And then what?
Right.
Like the universe just flicked a switch.
Sort of, yeah. As this massive cloud began to contract under its own gravity, a basic principle of physics kicked in conservation of angular momentum.
Ah, right.
It caused it to flatten into a spinning disk, a protoplanetary disk.
Yeah.
Picture like a skater pulling their arms in to spin faster, but, on an astronomical scale.
Okay, got it.
And inside this swirling disk, tiny particles started bumping into each other and sticking together. It's a process called accretion.
Accretion.
And that gradually formed the first planetesimals, kind of the basic building blocks of planets.
So these tiny specks, just countless gentle bumps, eventually grew into something real, almost like watching dust motes in sunlight slowly gathering.
That's a great way to put it. And this accretion kept going for millions of years, eventually forming Earth. But the early story takes another incredibly dramatic turn.
Okay.
Around 4.527 billion years ago, the giant impact hypothesis.
Ah, yes, the moon maker.
Yeah.
This one always just bowls me over.
Yeah, the sheer scale of this collision is just staggering. A Mars-sized object, sometimes we call it Theia, slammed into the young Earth.
Mars-sized.
The energy released was almost beyond imagining. Orders of magnitude greater than anything we can really picture.
Wow.
This impact wasn't just a nudge, it probably vaporized huge amounts of the early Earth's crust and mantle, basically remelted both bodies.
Vaporized rock.
So yeah, a collision powerful enough to do that didn't just create our moon, it fundamentally reset the conditions on the young Earth. A truly dramatic origin.
So not just a bump, but a planet-altering smash-up. And our moon, that familiar face in the sky, was born from the stuff thrown out.
Exactly. A huge amount of mantle material got blasted into Earth's orbit.
Right.
And gravity just relentlessly pulled this ejected stuff together to form our moon. This violent start also explains why the moon doesn't have much iron or those iron-loving elements.
Why is that?
Because the heavier core of Theia, the impactor, probably merged with Earth's own core during the collision.
Incredible. So right after this huge impact, what was early Earth like? I'm picturing just a boiling ball of molten rock.
It's a pretty good picture, yeah. Early Earth was incredibly hot, a giant ocean of molten rock, metals, minerals, all flowing freely. And this extreme heat led to a crucial process. Differentiation.
Differentiation?
Yeah, the denser stuff like iron and other elements that like to bond with iron.
Hydrophiles.
Right, siderophile elements, they sank towards the planet's center. Lighter, silicate-rich stuff floated to the top.
Makes sense.
Within the first maybe 10 million years of Earth's existence, the sorting created our planet's layered structure, that dense metallic core and the less dense silicate mantle. And this early differentiation was also key for generating Earth's magnetic field.
Okay, so this molten ball starts separating into layers, and somehow that creates this invisible magnetic shield. How exactly does that work?
Well, it's tied to the movement of electrically conductive material, molten iron, in the liquid outer core.
Ah, the liquid part.
Right. This movement, driven by heat escaping from the solid inner core, creates electric currents. And, basic physics tells us moving electric charges create magnetic fields.
Right.
This field, which really got established around 3.5 billion years ago, has been absolutely vital. It protects our atmosphere from the constant solar wind.
Solar wind.
Yeah.
The charged particles from the sun.
Exactly. This invisible shield has been deflecting potentially atmosphere-stripping radiation for billions of years.
That's just amazing. This unseen force, our silent guardian for eons. What about the air we breathe, the oceans covering everything? When did they show up?
The early atmosphere came about through outgassing. Gases trapped inside the Earth were released by volcanoes.
Oh, like volcanic burps, basically.
Well, pretty much. And this early atmosphere was likely very different. Lots of hydrogen, helium, carbon dioxide. Not much like today.
Right.
Then, as the planet slowly cooled, water vapor in that atmosphere condensed. It rained and rained, forming the first ocean.
Just from condensation.
Well, that process might have gotten a big boost from ice delivered by comets and asteroids crashing into early Earth.
Ah, so space deliveries of water.
It's possible, yeah. These celestial visitors might have played a really crucial role in filling up our oceans.
So these space travelers potentially brought water, maybe other elements too. It's also connected, isn't it? Like a grand cosmic dance.
It really is. And that early atmosphere, with more CO2, actually played a key role.
How so?
It stopped the young oceans from freezing over. The sun was significantly fainter back then, you see.
Oh, right. Faint young sun paradox.
Exactly. So this early greenhouse effect kept Earth warm enough for liquid water.
Fascinating. And while all this is happening, the surface itself is constantly changing, right? Continents moving around, crashing, splitting apart over huge timescales.
Absolutely. Plate tectonics. The idea that Earth's outer shell, the lithosphere, is broken into these large, rigid plates that move and interact.
Floating on a layer beneath.
Essentially, yes. Floating on the more ductile asthenosphere. Continents have clumped together into supercontinents like Rodinia, Pannotia, and the famous Pangaea, only to break apart again.
Driven by the Earth's internal heat.
Exactly. Driven by that heat. This constant reshaping has sculpted our landscapes, built mountains, carved out ocean trenches. It's Earth's internal engine constantly at work.
Like a geological ballet on a planetary scale, as you said. Okay, so from a fiery, molten start, through giant impacts, oceans forming, atmosphere building, we get to a planet with layers and a moving surface. Now let's zoom in on today, the physical stats of our home. What's its actual shape and size?
Well, we often picture a perfect sphere, but Earth's rotation makes it bulge out a bit at the equator.
Yeah.
So its shape is closer to a slightly squashed ball, or what scientists call a geoid. Basically, the shape that follows means sea level.
A geoid, okay.
And this bulge means the diameter across the equator is about 43 kilometers wider than the diameter pole to pole.
So not perfect, but close.
Yeah.
It's got a bit of an equatorial spare tire.
Yeah, you can put it that way. Size-wise, the average diameter is around 12,742 kilometers. Circumference at the equator is roughly 40,000 kilometers.
40,000 kilometers.
And interestingly, the definition of the meter was originally tied to Earth's size.
Oh, yeah?
Yeah, it was meant to be 1/10,000,000th of the distance from the equator to the North Pole, measured through Paris. A kind of testament to early efforts to measure our world.
That's a great historical link. And surface area. How much is land versus water? That blue marble image really sticks.
Yeah, it does. Total surface area is about 510 million square kilometers. Of that, roughly 29.2% is land, continents, and islands.
And the rest, water.
A vast majority, 70.8%, is covered by water, mostly the interconnected world ocean. That space view really nails the dominance of water.
It sure does. And what about mass? How heavy is our home planet?
Earth's mass is, well, it's huge. 5.97 times 10 to the 24 kilograms. That's a 5 followed by 24 zeros.
Wow.
This massive weight makes it the densest planet in our solar system. Average density is about 5.5 grams per cubic centimeter.
Densest? Why so dense?
That high density, much denser than typical surface rocks, points directly to the heavy metallic core at its heart.
Right, the iron core. Wow, that is dense. So what exactly makes up this huge mass? What are Earth's main ingredients?
By mass, Earth is mostly iron, about 32.1%. Then oxygen at 30.1%, silicon at 15.1%, and magnesium at 13.9%.
Iron first. That's surprising.
Oh, remember the core. It's predominantly iron with some nickel and sulfur. The crust, the thin layer we live on, that's dominated by oxygen and silicon, chemically bonded in silicate minerals.
So a surprisingly iron-rich world deep down. Now, we touched on the layers earlier, but let's go a bit deeper inside. What are the key layers and their features?
Okay, starting from the outside, we have the crust. Thin, rigid outer layer. Under the oceans, it averages only about 6 kilometers thick.
Only 6 kilometers. Wow.
Yeah, but under continents, it's much thicker, 30 to 70 kilometers. And it's divided into two main types. Oceanic crust, denser, mostly basalt.
And continental?
Continental crust is less dense, more varied, includes granite. The boundary between the crust and the mantle below is called the Mohorovicic discontinuity, or MOHO for short.
Mohorovicic.
It marks a sharp jump in seismic wave speeds, indicating a change to denser mantle rock.
Okay, the Moho discontinuity, and beneath that is the mantle, the bulk of the Earth.
Exactly. The mantle's this thick, silicate-rich layer going down to about 2,900 kilometers. It makes up something like 67% of Earth's total mass.
2/3 of the planet.
Pretty much. It's divided into upper and lower mantle, and within the upper mantle, there's a crucial zone called the asthenosphere.
Asthenosphere, that's the softer layer.
Yeah, slightly lower viscosity compared to the rock above and below. It's this relative softness that allows the rigid lithospheric plates above it to actually move.
Got it. And finally, right at the heart of it all, the core. Tell us about that deep, hidden realm.
The core is the central part, mostly iron and nickel. It's split into two sections. A solid inner core, with a radius of about 1,220 kilometers.
Solid, despite the heat.
Because of the immense pressure. And surrounding that is a liquid outer core, extending out to a radius of about 2,250 kilometers.
And the liquid outer core is key for the magnetic field.
That's the one. The churning motion of that molten iron in the outer core generates Earth's magnetic field. We call it the geodynamo process.
A solid ball inside a liquid one, generating a magnetic field. Amazing. And I know it's incredibly hot down there. Where does all that internal heat come from?
Two main sources. First, there's leftover heat from Earth's formation, the primordial heat.
From accretion and that giant impact.
Exactly. All that energy released back then, that still accounts for maybe 20% of the heat flow now.
And the rest.
The other big contributor is radioactive decay. Unstable isotopes like potassium-40, uranium-238, uranium-235, thorium-232 deep inside Earth.
Natural nuclear reactors.
In a way, yes. They have incredibly long half-lives, so they've been slowly releasing heat for billions of years.
So leftover formation energy plus ongoing radioactive decay. Just how hot does it get in the core?
Estimates put the temperature at the very center around 6,000 degrees Celsius.
6,000 degrees. Hotter than the sun's surface.
It is. And the pressure is equally immense, about 3.6 million times the atmospheric pressure we feel at the surface.
Unbelievable. That extreme heat and pressure must drive some powerful processes. How does that internal energy eventually get out?
Heat escapes through several key ways. Plate tectonics is a big one. Hot mantle material rising at mid-ocean ridges releases a lot of heat as new crust forms.
Okay.
Heat also comes up through mantle plumes, think volcanic hotspots like Hawaii.
Right.
And finally, there's just gradual heat loss through the lithosphere itself. More escapes through the thinner oceanic crust than the thicker continental crust.
So this internal heat, left over from birth and from radioactivity, it's not just sitting there, it's driving everything we see on the surface, like plate tectonics.
Precisely. It's the engine behind so much of Earth's dynamic activity.
Okay, we've looked at origins, physical stats, the inside story. Now, let's focus on our dynamic Earth. The process is constantly reshaping things. We've mentioned it, but can you break down plate tectonics a bit more?
Sure. Plate tectonics basically is the theory that Earth's rigid outer layer, the lithosphere, is broken into these pieces, these plates. About a dozen major ones and some smaller ones.
A giant jigsaw puzzle.
Kind of, yeah. And these plates aren't static. They're constantly moving very slowly, driven by the internal heat we talked about. They glide on the semi-molten asthenosphere below.
And where they meet, that's where the action is.
That's where you get intense geological activity. Earthquakes, volcanoes, mountain building.
So what kinds of boundaries are there?
3 main types. Convergent boundaries, where plates collide.
Like India hitting Asia.
Exactly, creating the Himalayas. If an oceanic plate hits a continental one, the denser ocean plate dives under that subduction, creates deep ocean trenches and volcanoes.
Okay, convergent. What else?
Divergent boundaries, where plates pull apart, most common at mid-ocean ridges. Molten rock wells up, creates new seafloor.
Spreading centers.
Right. And finally, transform boundaries, where plates slide horizontally past each other, like the San Andreas Fault in California. Lots of friction, big earthquakes.
Got it. And these plates, like the Pacific Plate, North American, Eurasian, how fast do they actually move?
It varies. Some move just a few millimeters a year, others up to maybe 75 millimeters, roughly the speed your fingernails grow.
Speed. It's amazing to think these huge slabs are constantly grinding past each other, shaping everything over millions of years. Okay, next up, the lifeblood water, the hydrosphere. It's arguably what makes Earth, well, Earth.
Absolutely. The sheer abundance of liquid water on the surface is a defining feature, key for life as we know it.
And most of it's in the oceans, right?
Overwhelmingly. About 96.5% is in the global oceans.
Yeah.
Massive reservoir. Smaller amounts are in rivers, lakes, groundwater, the atmosphere. And a significant chunk of fresh water is locked up as ice, the cryosphere. Poles, glaciers. Oh, and the average ocean salinity is about 3.5% salt.
And these huge oceans, they play a massive role in our climate, don't they?
Oh, completely. They act as enormous heat sinks. They absorb vast amounts of solar energy and distribute it around the globe via currents.
Moderating temperatures.
Exactly. Keeps coastal areas generally milder than deep inland. Major currents, like the big ocean conveyor belt, the thermohaline circulation.
Driven by temperature and saltiness.
Right. That plays a huge role in moving heat around, influencing weather patterns globally.
It's such a complex, connected system. Okay, from liquid to gas, the atmosphere, the air sustaining us. What's it made of? How's it structured?
Earth's atmosphere is this relatively thin but absolutely crucial gaseous layer, mostly nitrogen, about 78%.
Not oxygen.
Oxygen is second, about 21%. Then small amounts of argon, about 0.9%. And then tiny but important amounts of carbon dioxide, around 0.04% currently, plus water vapor, which varies a lot.
And life changed the atmosphere over time.
Profoundly. Especially the rise of photosynthesis, pumping out oxygen. The atmosphere also has layers. Closest to us is the troposphere. That's where all our weather happens.
Okay.
Above that, the stratosphere, holding the vital ozone layer.
Blocking UV rays.
Exactly. Then the mesosphere, which is the coldest layer. Above that, the thermosphere, where auroras happen. Then the ionosphere, full of charged particles. And finally, the exosphere, where gases can escape to space.
And this atmosphere blanket does way more than just give us oxygen.
Oh, yeah. It regulates temperature through the greenhouse effect. Without it, Earth would be frozen solid.
Right.
It shields us from harmful solar radiation, burns up most incoming meteoroids, drives weather, the water cycle. It's a delicate, dynamic system vital for life.
And speaking of life, let's touch on the biosphere, the zone of living things. How has life itself shaped our planet?
Well, the biosphere includes all life, and it interacts constantly with the rock, water, and air. Life probably emerged pretty early, maybe 3.5 to 3.9 billion years ago. We talk about the last universal common ancestor, or OECA. A key moment was photosynthesis evolving, especially oxygenic photosynthesis, around 2.5 billion years ago. That started pumping oxygen into the atmosphere.
The Great Oxidation Event.
Right, a kind of pollution that ultimately allowed complex oxygen-breathing life to evolve. Earth's also seen dramatic climate shifts, like snowball Earth events where it might have frozen over completely, followed by things like the Cambrian explosion, a sudden burst of diverse multicellular life, and of course several mass extinctions have totally reshaped life's course.
And now humans are having a huge impact.
An unprecedented and accelerating impact, yes.
The constant back and forth, isn't it? Life adapting to Earth and life changing Earth. Okay, let's shift perspective outwards. Our orbit, our rotation, how do they affect daily life and the seasons?
Earth orbits the sun in an ellipse, not a perfect circle. Average distance is about 150 million kilometers. We're moving at nearly 30 kilometers per second.
That's fast.
It is. One full orbit takes about 365 and a quarter days. That defines our year.
The quarter days for leap years, right?
Right. That's why we need them, yes, to keep the calendar synced. Earth also spins on its axis, west to east. One rotation takes about 23 hours, 56 minutes, and 4 seconds. That's a sidereal day.
Slightly less than 24 hours.
Right. The 24-hour solar day accounts for our movement around the sun, too.
And the seasons. That's the tilt.
Yes, the tilt of Earth's axis. It's currently about 23.44 degrees relative to our orbital plane.
Not straight up and down.
No. And as Earth orbits, this tilt means different hemispheres get more direct sunlight at different times of the year. That causes summer, autumn, winter, spring, the solstices and equinoxes.
Ah, the familiar rhythm, all down to that tilt. And we can't forget the moon. How does it interact with us?
The moon orbits Earth roughly every 27.3 days. Its gravity is the main driver of our ocean tides.
High tide, low tide.
Exactly. But interestingly, the moon also helps stabilize Earth's axial tilt over long timescales.
Stabilizes the tilt. How?
Its gravity sort of prevents Earth from wobbling too erratically, which could cause really drastic climate swings.
Wow, okay.
And over millions of years, the moon's gravity is actually gradually slowing down Earth's rotation. Days used to be shorter.
So the moon isn't just pretty. It's an active partner in Earth's stability and cycles. Now, looking way, way ahead, the future of Earth. It's hard to imagine it not being here.
Well, Earth's distant future is totally tied to the sun's evolution. As the sun ages, it gets brighter.
Brighter.
Yes, its luminosity gradually increases. In about 1.1 billion years, this extra solar radiation could heat Earth's surface enough to start evaporating the oceans.
Evaporating the oceans. That's a sobering thought. Our life-giving water, gone. What else is in store?
Further out, maybe 500 to 900 million years from now, the rising temperatures speed up rock weathering.
Okay.
This process pulls CO2 out of the atmosphere. Eventually, CO2 levels could drop too low for most plants to survive.
No plants.
Which means oxygen levels would plummet too, making Earth uninhabitable for most animal life, probably within a few million years after the plants go. By about 3.5 billion years from now, conditions here could be like present-day Venus. Oceans totally gone, hot, barren surface.
Like Venus. Hard to picture.
It's humbling, isn't it? The sunlight that sustains us now will eventually be what makes the planet uninhabitable, a real cosmic perspective.
It really is hard to conceive of an Earth without life, without oceans, like an alien planet.
And the story gets even bigger. Around 7 billion years from now, the sun runs out of hydrogen fuel in its core and enters its red giant phase.
It swells up.
Dramatically. It could expand enough to actually engulf Earth, or at least reach our current orbit.
Engulf us.
It's a possibility. Even if Earth survives being swallowed, the surface would become molten rock again.
Back to the beginning almost.
In a way. And after the red giant phase, the sun collapses into a white dwarf, a dense, cooling ember. Earth, if it's still around, would become a cold, dark, frozen rock.
An epic, almost tragic story on a cosmic scale. Vibrant world to dark wanderer. Okay, shifting gears a bit. What about the cultural significance of Earth? How have people viewed our home?
Well, the name itself, Earth, in English, comes from Old English eorth, meaning ground or soil.
Ah, very earthy.
Exactly. And unlike the other planets named after Greco-Roman gods, Earth has this more grounded origin.
That is interesting. And we have those astronomical symbols too, right?
Yes, the circle with a cross inside, representing the cardinal directions, or a circle with a plus sign below it, like a globe with a cross on top, the globus cruciger.
Sure.
And throughout history, so many cultures have personified Earth, often as a goddess or mother figure.
Another Earth.
Right. Tonantzin for the Aztecs, Hutu in China, Gaia in Greece, Jorda in Norse myths. Even the male god Gib in ancient Egypt represented Earth.
So a deep recurring connection, seeing Earth as nurturing. What about understanding its shape? We know it's a geoid now, but that took time.
Oh, definitely. Many ancient cultures thought Earth was flat. Early Mesopotamians saw it as a flat disk on a cosmic ocean.
Flat Earth.
But as early as the 6th century BCE, Greek philosophers like Pythagoras suggested a sphere. Aristotle later offered observational evidence.
Like ships disappearing hull first over the horizon.
Exactly, and Earth's curved shadow on the moon during an eclipse. This spherical idea gradually spread, but it wasn't really until the age of exploration and then definitively spaceflight that we got direct visual proof.
The pictures from space.
Absolutely. That iconic blue marble photo from Apollo 17 in 1972, it had a huge impact. Showed our planet as finite, fragile.
And Carl Sagan's pale blue dot.
Yes, from Voyager 1, looking back from the edge of the solar system. Just incredibly humbling. Changed our perspective.
Those images really did revolutionize how we see ourselves, didn't they?
Yeah.
Showing Earth as this interconnected, vulnerable oasis. And that's fostered ideas like the Gaia hypothesis.
Right. The Gaia hypothesis from James Lovelock suggests Earth's living and non-living parts act like a single self-regulating system.
Keeping conditions right for life.
Essentially, yes.
Yeah.
It emphasizes how the biosphere, atmosphere, oceans, rocks are all tightly linked, interacting to regulate temperature, air composition, etc. It really highlights that interconnectedness.
It really does all come full circle, doesn't it? From the planet's formation through all these huge geological and biological changes to how we see it, how we understand this intricate web. It's been an absolutely amazing journey through time and space today.
It really has. I think what stands out most is just the sheer scale of time involved. Billions of years of cosmic events, geological shifts, life evolving, all woven together.
Yeah.
And when you grasp how interconnected everything is, the core generating the magnetic field, the atmosphere controlling climate, life shaping the air, you just get this profound appreciation for this incredible planet.
It truly makes you think about our place in the cosmos, doesn't it?
Yeah.
Seeing Earth in that huge context as this unique, precious home for life.
Absolutely. And hopefully this whole discussion has maybe sparked a deeper sense of wonder, maybe even responsibility towards the planet we call home. You know, just take a moment sometime, look at the rocks around you, notice the weather patterns, gaze up at the night sky. They're all constant reminders of the incredible forces and processes that made and still make our world.
So as we finish up, maybe leave you with this thought. Just ponder the sheer improbability, the immense value of this pale blue dot, this amazing planet that's nurtured life for billions of years. It's a powerful reminder, isn't it, of both its fragility against cosmic forces and the vital role we play as its current inhabitants.
Ever just look up at the stars and get that feeling? You know, that sense of just how much is out there that we don't understand.
Oh, absolutely. It's humbling.
And for me, black holes. They've always been the peak of that mystery. Are they just like giant vacuum cleaners or something weirder?
Nothing much weirder, I think it's fair to say.
Yeah, that first image we saw, you know, from M87, that fuzzy orange donut.
Incredible moment, a real landmark.
It felt like more than just a picture. It was like staring into, well, something truly fundamental.
It really was, taking it from pure math, from equations, into something we could actually see.
Exactly. So today, let's really get into it. Go beyond that image.
Let's do it. We can trace the whole story, right? From the earliest kind of speculative ideas.
All the way to how we actually find them now and some of the really mind-bending physics involved.
Yeah, the stuff that makes them tick. It's quite a journey.
Okay, so this isn't just going to be us reading facts. We're following the clues, seeing how this picture built up over time.
And hopefully connecting some dots, maybe uncovering a few surprises for you along the way.
Right, so buckle up. We're heading to the edge of known physics here. Space, time, gravity, the big stuff.
And believe it or not, the story starts way back. 1784. A guy named John Mitchell.
1784, wow, okay. What was his idea?
He called it a dark star. Basically, an object so massive, so dense, that its escape velocity would be faster than the speed of light.
So light couldn't even escape.
Exactly. He even calculated, you know, a star maybe 500 times the sun's radius, but same density, it would be invisible. Completely dark.
That's wild, using Newtonian physics. Before Einstein?
Yep, and Laplace, the French mathematician, he picked up on the idea too, for a bit.
So why didn't it take off? Why wasn't everyone talking about dark stars in the 1800s?
Well, the key thing was the speed of light. Back then, it wasn't really seen as this absolute universal speed limit.
Okay. So the idea of light being trapped didn't have the same, like, fundamental implications.
Exactly. Classical physics didn't forbid things going faster than light, really. It wasn't until Einstein came along with special relativity.
And established c is the ultimate speed limit.
Precisely. Suddenly, Mitchell's idea looked a lot more profound. And that realization that light speed was fundamental kind of paved the way for needing a new theory of gravity.
Which brings us to general relativity. GR.
The bedrock. Our modern understanding of black holes rests entirely on Einstein's GR.
And GR basically says gravity isn't a force pulling things. It's about space-time itself being warped.
You got it. Mass and energy curve spacetime. Think of the classic analogy. A bowling ball on a rubber sheet.
Right, and marbles rolling nearby follow the curve.
Exactly. And locally, like on a tiny patch of that sheet, it still looks flat, just like space-time looks flat in our immediate vicinity, even though Earth is curving it.
It's like the Earth looking flat from your backyard, but you see the curve over the horizon.
Perfect analogy. Or imagine parallel transporting an arrow on a sphere. You move it carefully, keeping it parallel to itself along the path.
But when you get back to the start, it might be pointing differently.
Right. Because of the sphere's curvature, space-time curvature works similarly. And it's the solutions to Einstein's GR equations that predict these regions of extreme curvature, black holes.
Okay, so GR predicts them. Now, I've heard this phrase, black holes have no hair. What on earth does that mean?
It's a great phrase, isn't it? Attributed mostly to John Wheeler.
Wheeler, right.
It summarizes the no-hair theorem. Basically, once a black hole forms and settles down, it becomes incredibly simple. All the messy details of whatever collapse to make it gone.
Like it forgets its past.
In a way, yes. From the outside, you can only measure 3 things about a stationary black hole. Its total mass, its total angular momentum, its spin, and its total electric charge.
Just 3 things. That's it for these cosmic monsters.
That's it, like a cosmic barcode. Mass, spin, charge.
Wow. Okay. And these 3 properties lead to different types of black holes in the theory.
Exactly. The math gives us 4 main stationary solutions based on those properties.
Okay, what are they?
Simplest is Schwarzschild. No spin, no charge, just mass. That was the first exact solution found.
The classic basic black hole.
Then Reisner-Nordstrom. It has charge but no spin.
Okay.
Then Kerr. This one spins but has no charge. This is actually the most important one for astrophysics.
You're right. You'd expect things in space to be spinning.
Absolutely. And finally, the most general one, Kerr-Newman. It has mass, spin, and charge.
So why is the Kerr one, the spinning but uncharged one, the most relevant?
What?
Why not the charged ones?
Good question, because in space, if a black hole somehow formed with a lot of electric charge, it would very quickly attract oppositely charged particles and gas from its surroundings.
So it would neutralize itself, like static electricity discharging.
Pretty much, yeah. So astrophysically, we expect most black holes we see out there to be spinning, maybe quite fast, but essentially electrically neutral, making the Kerr solution the best fit for reality.
Okay, let's dive into that simplest one first, the Schwarzschild black hole. No spin, no charge. What defines it?
2 key concepts emerge from the Schwarzschild solution: the event horizon and the singularity.
The point of no return and the point where physics breaks.
That's a good way to put it. The event horizon is this boundary. Cross it and you're trapped. Escape velocity becomes greater than the speed of light, no going back.
And the singularity.
That's the theoretical point right at the center where the curvature of spacetime becomes infinite, density becomes infinite. Our current physics, GR included, can't describe what happens right at the singularity.
And the size of that event horizon, that boundary, is the Schwarzschild radius.
Correct. It's calculated with a surprisingly simple formula. 3SL equals 2gm over squared. G is the gravitational constant, m is the mass, c is the speed of light.
Give me a sense of scale, like for Earth.
If you compress the Earth down to its Schwarzschild radius, it'd be about 9 millimeters across. A marble.
Seriously, 9 millimeters.
Yeah, and the sun. About 3 kilometers radius, roughly the size of a small town.
Mind-blowing. And you mentioned earlier, even Newton's gravity kind of predicts this radius.
It's a fascinating coincidence, yeah. If you calculate the radius where escape velocity equals light speed using classical mechanics, you get the same 2gmc2 torus. Doesn't mean Newton was right about the y, but the number pops out.
Weird. Okay, what about density? You'd think they're infinitely dense, but...
Well, the singularity is theoretically infinitely dense, but the average density within the event horizon is different, and it actually decreases as the black hole gets more massive.
Wait, hang on. Bigger black holes are less dense on average.
Counterintuitive, right? A solar mass black hole would have an average density higher than an atomic nucleus, but a supermassive one. Billions of solar masses. Its average density inside the horizon could be less than water.
Less dense than water.
Yeah.
But still inescapable.
Because the total mass and the resulting spacetime curvature are what matter for the horizon, not just the density. So these giant black holes can be surprisingly fluffy on average.
Okay, fluffy black holes, got it. You also mentioned a coordinate singularity at the event horizon. That sounds technical.
It is a bit. Basically, in the original way Schwarzschild wrote down his solution, the math looks like it breaks at the event horizon. things go to infinity.
Like the real singularity at the center.
No, that's the crucial difference. This one at the horizon is just an artifact of the coordinate system being used, like how longitude lines all converge weirdly at the North Pole on a map.
So the map is weird there, but the actual North Pole is fine.
Exactly. Space-time itself is perfectly smooth at the event horizon for someone falling through. It's not a physical barrier or edge in that sense.
So, what is beyond the horizon in this Schwarzschild picture? Does space-time just stop?
Not according to the math. If you use different coordinates, like Kruskal-Seker's coordinates, you find the space-time continues. This leads to the maximally extended Schwarzschild space-time.
Sounds complicated. What does that look like?
It's wild. It suggests our universe, region 1, is connected through the black hole interior, region 2, to potentially another universe, region 3.
Another universe. Seriously.
Mathematically, yes. And there's also a theoretical structure connecting region I and region the third called an Einstein-Rosen bridge.
A wormhole. Like in the movies.
The very same concept. A theoretical shortcut through space-time.
Can we?
Use it. There's the catch. For the Schwarzschild wormhole, no. If you fall in from our universe, you inevitably hit the singularity in region 2. You can't reach a region the third.
Okay, so no interuniversal travel agency then.
Not with this model. Plus, this wormhole isn't stable. Those diagrams showing its evolution, the connection, the throat, pinches off extremely quickly. It's a fleeting theoretical bridge, not a traversable tunnel.
Fascinating, but ultimately theoretical dead ends, maybe. What about the other types? The charged or spinning ones, do they have similar weirdness?
They do, often even more complex. Reisner-Nordstrom, the charged, non-spinning one, its extended space-time also hints at multiple connected universes. But it has inner and outer horizons, and structure depends on the charge.
Is there a limit to the charge?
Yes. If the charge gets too large relative to the mass, the event horizons disappear entirely, leaving a naked singularity. Most physicists think nature prevents this via something called cosmic censorship.
Naked singularities sound bad.
They break predictability, yeah. And again, charge tends to get neutralized anyway.
Right. So, the spinning Kerr black holes, they're the ones we expect to see. What's special there?
Kerr black holes introduce the ergosphere. It's a region outside the event horizon.
Outside, so you can escape it.
Yes, but inside the ergosphere, space-time itself is dragged around by the black hole's spin so intensely that you cannot stay still relative to a distant observer. You must rotate with the black hole.
Forced co-rotation. Wild.
And interestingly, you can theoretically extract energy from the black hole's spin by flying through the ergosphere in a clever way, the Penrose process, like a cosmic energy source.
Free energy from a black hole. Okay, now it's getting really sci-fi.
Again, theoretically possible. Like Reisner-Nordstrom, Kerr also has limits on its spin to avoid naked singularities, and the Kerr-Newman solution with spin and charge.
The most general one.
It combines features of both Kerr and Reisner-Nordstrom, ergosphere, multiple horizons. Its extended space-time geometry is incredibly complex, also hinting at connections and potential time loops, but again, with lots of caveats about stability and traversability. It's the full mathematical playground.
It's amazing that just mass, spin, and charge can lead to such intricate theoretical structures, but it all still feels very black. Until Hawking, right?
Exactly. The idea that black holes are perfect absorbers, one-way membranes, got a massive shakeup in the 70s. Starobinsky, Zeldovich, and especially Stephen Hawking.
Hawking radiation, the idea that black holes aren't completely black.
Precisely. Hawking used quantum field theory in curved space-time near the event horizon and showed that black holes should actually emit particles, a faint thermal glow.
But if nothing can escape from inside the horizon.
The radiation doesn't come from inside, it's generated just outside, in the quantum vacuum. Think of virtual particle-antiparticle pairs constantly popping into existence and annihilating.
Quantum fuzziness.
Right. Near the horizon, the intense gravity can pull one particle of a pair in before it annihilates, while the other escapes.
And the escaping one carries energy away.
Exactly. To an outside observer, it looks like the black hole just emitted that particle, but the energy ultimately comes from the black hole's mass. EMC squared.
So the black hole shrinks, it evaporates.
Very, very slowly, yes. Hawking derived the formulas, the power radiated, the mass loss rate. They depend inversely on the square of the mass.
Meaning smaller black holes radiate more.
Much more intensely. And because it's thermal radiation, it means black holes have a temperature and even entropy.
Temperature, entropy, for a black hole. That just sounds wrong.
It blew people's minds. It connects gravity, quantum mechanics, and thermodynamics, a huge theoretical leap.
So what are the consequences? Small black holes evaporate faster.
Much faster. A tiny primordial black hole, if one existed, could evaporate completely in a final explosive burst. But a big stellar mass or supermassive black hole, its temperature is incredibly low.
Lower than what?
Lower than the temperature of the cosmic microwave background radiation, the faint afterglow of the Big Bang that fills space.
So, wait. If they're colder than their surroundings.
They absorb more energy from the CMB than they radiate away via Hawking radiation. So right now, the big black holes are actually still growing, not shrinking.
Okay, so evaporation is only really relevant for hypothetical tiny black holes, or way, way in the future when the universe cools down more.
Pretty much, yes. For astrophysical black holes today, accretion and mergers are dominant.
And what happens at the very end of evaporation? When it gets down to the quantum scale?
That's the million-dollar question. Or maybe billion-dollar. We don't know. Our theories break down. We need a full theory of quantum gravity.
Right, the theory of everything. Still searching.
Still searching. Does it vanish? Leave a tiny remnant. We need new physics to answer that.
Okay, shifting from theory back to experience. Hypothetically, what's it like falling into one? Say, a big supermassive one where tidal forces aren't instantly lethal at the horizon.
Well, from your perspective, the person falling in, crossing the event horizon itself, would be surprisingly uneventful. Locally, nothing special happens at that exact moment.
No flashing lights. No welcome to the singularity sign.
Afraid not. You'd be in free fall, so you'd feel weightless. The real trouble comes later.
Tidal forces. Spaghettification.
Exactly. The difference in gravity between your head and your feet would stretch you out while you get squeezed sideways. Closer to the singularity, these forces become infinitely strong. Not a good end.
Definitely noted. But what about my friend watching safely from a spaceship far away? What do they see?
Their view is completely different. As you approach the horizon, they see your clock ticking slower and slower relative to theirs. Gravitational time dilation.
Time slows down for me from their perspective.
Massively. And the light from your flashlight, say, would get stretched to longer, redder wavelengths. Gravitational redshift.
Do I look like I'm slowing down, getting redder?
Yeah, and dimmer. As you get extremely close to the horizon, you'd appear to almost freeze there, getting infinitely redshifted and fading away.
So they never actually see me cross the horizon.
Never. From their perspective, it takes an infinite amount of time for you to reach it. You just seem to hover there, fading into oblivion.
And any information I was carrying, just lost to them.
Effectively, yes. The light becomes undetectable. This leads to the whole information paradox puzzle we mentioned with Hawking radiation. Does the information truly vanish, or is it encoded somehow?
Like maybe on the horizon itself?
That's one idea, the holographic principle. Very cutting-edge stuff. And this visual effect, the freezing and fading, it's similar to how we'd observe a star collapsing to form a black hole. It would just fade out.
Okay, so the theory's wild, the experience is unpleasant. How do we know these things are actually out there? What's the evidence?
The evidence now is really, really strong. Overwhelming, I'd say. We think they form in several ways.
Like dead stars?
That's the main way for stellar mass black holes. A really massive star runs out of fuel, the core collapses. Boom. If the core is heavy enough, more than about 2.5 to maybe 5 times the sun's mass, above the limit for neutron stars, gravity wins completely.
And it collapses into a black hole just a few miles across.
Something like that, yeah. Very compact.
And the supermassive ones. The galaxy center monsters.
Their origin is still debated a bit. Maybe giant gas clouds collapsing directly in the early universe. Maybe smaller black holes merging over billions of years. Probably a mix of things. And then there are the theoretical ones.
Primordial black holes from the Big Bang.
Potentially, yeah. Formed from density fluctuations right at the start. Could be tiny, could be huge. And maybe even tiny quantum black holes in particle colliders, though that's highly speculative.
Okay, so lots of ways they could form. But how do we spot them if they're black?
Indirectly. It's all about gravity's effects. The key is measuring mass and size. Find something incredibly massive packed into an incredibly small space.
Smaller than its calculated Schwarzschild radius.
Or gravitational radius, 5 regalers, which is the same formula, essentially. If the object's radius is comparable to or smaller than regalers for its measured mass, you've likely found a black hole.
And the best evidence is for the supermassive ones in galactic centers.
That's where the evidence is most robust, yes. Like Sagittarius A, Sag-A star, in our own Milky Way.
How do we measure the mass there? We can't put it on scales.
We watch things orbit it. Stars, gas clouds, we measure their speed, their orbital distance. Then Kepler's laws and Newton's gravity give you the central mass pulling the strings.
Like weighing the sun by watching the planets orbit it.
Exactly the same principle. We can also look at the overall distribution of star speeds near the center, or the mass-to-light ratio, finding a huge amount of mass in a region that's not very bright.
Dark mass.
Highly suggestive of a black hole. Plus, we can sometimes measure the size of the emitting region directly with radio telescopes and see if it matches the expected event horizon size.
Like with Sag.
Precisely. And tracking individual stars whipping around it. The star S2, for instance, has been tracked through a full orbit. That gave us a super precise mass for Sag, about 4.3 million solar masses, and the distance to the galactic center.
Wow. Just by watching one star fly around.
Incredible precision work. We also see stars getting torn apart if they stray too close, tidal disruption events, big flares of energy.
Messy eaters.
You could say that. And then the ultimate confirmation.
The pictures. The Event Horizon Telescope images.
Yes. M87 in 2019, Sag in 2022. Using a network of telesnips across the globe, effectively creating an Earth-sized dish.
They saw the shadow.
They saw the dark central region, the black hole's shadow cast against the bright, swirling hot gas around it. Direct visual evidence of the event horizon. A stunning confirmation of GR's prediction.
Just amazing. From Mitchell's dark star idea to actually seeing the shadow. What a journey. So where does the research go now? What are the frontiers?
Oh, tons of open questions. In the non-quantum realm, we're still figuring out the detailed structure of spinning black holes, how their horizons ripple and emit gravitational waves when disturbed.
Like when they merge. LIGO detections.
Exactly. That's a huge area. Studying those mergers tells us so much. Also, theoretical stuff like, could Kerr black holes allow closed time-like curves, time travel loops? And the chronology protection conjecture, does physics prevent that?
Whoa, time travel again. Okay. And on the quantum side?
That's where the really deep mysteries lie. The information paradox, where does the information go? Trying to understand Hawking radiation better, maybe even detect it someday, though it's incredibly faint for big black holes.
What about the final evaporation stage?
Still a huge unknown. What are the properties of quantum black holes, if they exist? How would they interact with particles? It's all tied into finding that theory of quantum gravity.
So it sounds like black holes are kind of the ultimate laboratory for testing the limits of our theories.
They absolutely are. Where gravity is strong and quantum effects should matter.
Okay, so what are the biggest unresolved problems right now, the major hurdles?
Well, a formal proof of cosmic censorship that singularities are always hidden, still needed. A completely general proof of the no-hair theorem for all conditions, still working on it.
Understanding black hole magnetospheres fully.
Yep, the plasma physics around them is complex. Finding the exact formula for their entropy in terms of quantum microstates, that's key for quantum gravity.
What's left after evaporation?
Still unknown. And proving the hoop conjecture rigorously, basically, a rule of thumb for when collapsing mass must form a black hole. Lots to do.
It's really humbling. We've learned so much, even imaged them, but the biggest questions seem to remain.
That's the beauty of science, isn't it? Each answer often reveals deeper questions.
Looking back, though, from those first dark star thoughts to GR to Hawking radiation to actually seeing them, it's a phenomenal story of discovery.
Truly, they're not just cosmic endpoints, they're active players, predicted by theory, confirmed by observation, and constantly challenging our deepest understanding of reality.
The idea of connected universes, even if unreachable, black holes having temperature, the link between gravity and quantum mechanics, it's just astonishing.
It forces us to rethink everything.
So here's something for you listening to think about. If information seems to fall into a black hole and vanish, could it be that it's not really gone? Maybe it's just stored or encoded in a way we can't yet read, perhaps on the event horizon itself.
The universe might be stranger and more subtle than we can currently imagine.
Definitely makes you wonder about the true nature of information, space, and time itself. What else is out there just waiting for us to figure out the right questions to ask?